Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the air compression refrigeration. As explained in Project 11.1, the Carnot cycle and the reversed Carnot cycle are identical, except that the reverse Carnot cycle operates in the reverse direction. This suggests in the power cycles discussed in earlier projects can be used as refrigeration cycles by simply reversing them. In fact, the vapor compression refrigeration cycle is essentially a modified Rankine cycle operating in reverse. Another example is the reversed Stirling cycle, which is the cycle on which Stirling refrigerators operate. In this task, we discuss the reversed Brayton cycle, better known as the gas refrigeration cycle. Consider the gas refrigeration cycle shown in figures 12.3 and 12.4. The surroundings are at T0 and the refrigerated space is to be maintained as TL. The gas is compressed during process 1 to 2. The high pressure, high temperature gas at state 2 is then cooled at constant pressure to T0 by rejecting heat to the surroundings. This is followed by an expansion process in a turbine during which the gas temperature drops to T4. Finally, the cool gas absorbs heat from the refrigerated space until its temperature rises to T1. All the processes described are internally reversible, and the cycle executed in the ideal gas refrigeration cycle. In actual gas refrigeration cycles, the compression and expansion process deviate from the isentropic ones, and T3 is higher than T0 unless the heat exchanger is infinitely large. On a TS diagram, the area under process curve 4 to 1 represents the heat removed from the refrigerated space, and the enclosed area 1, 2, 3, 4, 1 represents the network input. The ratio of these areas is the COP for the cycle, which may be expressed as the gas refrigeration cycle deviates from the reverse Carnot cycle because the heat transfer processes are not isothermal. In fact, the gas temperature varies considerably during heat transfer process. Consequently, the gas refrigeration cycles have lower COPs relative to the vapor compression refrigeration cycles or the reverse Carnot cycle. This is also evident from the TS diagram in the figure. The reverse Carnot cycle consumes a fraction of the network but produces a greater amount of refrigeration. Despite their relatively low COPs, the gas refrigeration cycles have two desirable characteristics. They involve simple, lighter components, which make them suitable for aircraft cooling, and they can incorporate regeneration, which makes them suitable for liquefaction of gases and cryogenic applications. An open-cycle aircraft cooling system is shown in the figure. Atmospheric air is compressed by a compressor, cooled by the surrounding air, and expanded in a turbine. The cool air leaving the turbine is then directly routed to the cabin. We now analyze the refrigeration coefficient for a gas refrigeration cycle. The heat absorbed isobarically from cold refrigerated space is. The heat transferred isobarically to warm environment is. The net work needed by the cycle then is. By definition, the refrigeration coefficient then is. Since the temperature for each state is, then the refrigeration coefficient can be simplified as the refrigeration coefficient for gas compression refrigeration or the reverse Brayton cycle is. The refrigeration coefficient for the reverse Carnot cycle is. For the same temperature limits T0 and Tc, we can conclude that the refrigeration coefficient for the reverse Carnot cycle is larger than that for the reversed Brayton cycle. For the reversed Brayton cycle working on the same temperature limits T0 and Tc, when the pressure ratio increases, the refrigeration coefficient decreases. However, the refrigeration capacity increases. Okay, that's all for this task. Thank you very much, and see you next time.